record. All right, and I'm going to share my screen because I have, since doing it last time, I have put it on my iPad, and it turns out I can annotate on the notes with my iPad. So you'll be able to see that easier on the system. So when we last met, we talked about DP, the degree of polymerization. We saw that in the stepwise polymers, because we would hook two monomers together and then two more monomers together, that the polymer, the molecular weight did not increase till the very, very end of the reaction. And by contrast, in the chain growth, because each individual chain is growing and adding on to it, we actually saw the DP increased much earlier and the monomer concentration deplete much slower than that of the step growth systems. Okay, and so the idea here is that number one, they have different mechanisms, they have different industrial uses, but you also have to be careful because the chain reactions can be done in minutes to an hour, where the step growth polymerizations might take days, because you have to wait for that diffusion to get the high molecular weight. So there's definitely, looking at that as an industrial process, such that you need to have the time to get the DP that you want, or the molecular weight you're trying to get to. All right, so then we now need to talk about naming. And naming is very complicated because a lot of times the IUPAC name, which is the International Union of Pure and Applied Chemistry, is very, very complex. But it's exactly precise. If you find the IUPAC name for a polymer, you can take it anywhere in the world and that will be it. However, they're almost never used because they can be very long, they can be very contrived, and nobody really uses. So most of the time we use the common polymer nomenclature, which are derived from the engineers who actually did the work. So there's several different ways to do it. The first and most common is to do the source base. Basically, what were the monomers going into the system? Okay, so that's really common, especially in the vinyl polymer system. So we'll see things like ethylene turn into polyethylene. Even though there are no double bonds, carbon-carbon double bonds in polyethylene, we still keep the name because that's what it started from. So that's the source-based name. Okay, now the other way to do it, especially in step growth polymers, is it's by the type of functional group. Remember, in the chain growth, we tend to have a carbon-carbon backbone. Okay, but in the step growth, we tend to have some other functional group in there, and so we tend to name the step growth ones by the functional group that is used to make that polymer grow. Okay, so the other thing we also do within polymer systems is parentheses mean a lot. So if you have a complex name, like in the case of polyethylene terephthalate here, what we're looking at here is that it's the polymer that contains both ethylene unit and a terephthalate unit. Okay, so this is an example of a step growth polymer. Terephthalate indicates it's a polyester. That's what the 8 means at the end here. So we have a polyester that's made from terephthalic acid and polyethylene or ethylene glycol. Now, in the case of the pentene here, it's just saying that the alkene, or the double bond, was on the end of the chain, which means we have all these little chains that are like 3 units long hanging off of the main polymer. And then if we go to something even more complex like this, methoxycarbonyl ethylene. So imagine you have a methoxy and a carbonyl and an ethylene on there. So you really are looking at something that looks probably like a polyacrylic ester. And so the idea is that that group is a subgroup hanging onto the main chain of the polymer, and it's a polymer here. So see, it's complicated. And so there are a few ones that we are going to get very familiar with and kind of need to use because they are the most common ones people will use for incorporating nanomaterials to change their properties. Okay, so a lot of times we'll see they're used like trade names. Like, so most people, when they look at polyethylene, a tetrafluoropolyethylene, they just say, oh, that's Teflon. Well, technically Teflon is a common name, and not all of the perfluorinated polymers actually are tetrafluoroethylene. So we have to be a little careful when we're looking at that, but we do need to know some of the common names because those are going to be the ones we'll see in the titles. Those are going to be the ones we're going to see in the use in the material section of a lot of the papers we'll be looking at. So we'll have to look at those trade names, but we also want to make sure that we want to avoid just saying, oh, you know, everything that's tetrafluoroethylene is Teflon, because it's really not. Okay. So then we have some that are more descriptive, that aren't true poly something names. We say things like it's a polycarbonate made from bisphenol A, or it's a polymer made from phenol formaldehyde, which is a cross-linked thermoset adhesive. So it's more describing what are in there, but not really calling it a polymer because of the structure there. So those can be a little challenging. And then there's a lot of acronyms that we'll see. In fact, when we'll, in just a few slides, we'll see that we have things like PEDF and PTEF, you know, and PETE, PET. All of those different acronyms actually mean something, and some of them are actually that mean the same thing. And so we have to be very careful about our acronyms we use. In fact, when we are going to write our paper or when we're going to have our presentation, you need to do like the whole name and then the descriptor or the acronym you're going to use for the rest of the talk. That would be preferred for everybody's help. And this also can be another way of getting a little weird, is the fact that you can use the same words to describe different types of polymers. So for example, in the case of this, we have polyethylene oxide. And so this means ethylene oxide was the unit there. And so imagine we're starting with an epoxy and we ring open that, we polymerize that. Well, we can also have this ethylene oxide, which is actually just a circular chain made from the dehydration of ethylene glycol. Or we can even have a block comonomer made by a couple different ways, where we have polyethylene, then a block with an oxygen here, so it's an oxide or an ether linkage, and then another polyethylene block. Okay, so all three of those are different polymers with different properties, but they can all be described with the same words. So that's why it's a little confusing. So we really need to be very precise about when we look at it, or when we find something that could be ambiguous. We need to kind of dig down and see where they got it, because sometimes they'll say, oh, from Aldridge, and then we can look it up and see what the exact structure is. So that's important too. And the other problem with the polymer names is because they're named by who makes them, they can name them based on how they made it, not necessarily what the final source is. So this one right here, polyethylene oxide, or PEG, a lot of people polyethylene glycol call it. Well, but it's polyoxyethylene, and you can use that if you're making it from some kind of ether synthesis, or polyethylene oxide if you're making it from a chain growth, I'm sorry, an anionic polymerization of epoxy. Or you can go from ethylene glycol right here. So you're making it from an ethylene with two alcohols on it, but then you're polymerizing it with something else. So they can all be the same polymer. They're just made by different companies from different starting materials. And so we have to be kind of careful when we're looking at these things. In addition to that, this one right here, this is commonly known as nylon 6. Well, the nylon 6, or a 6-membered ring with an amide in it, is also called caprolactam. So some people call it polycaprolactam, or epsilon caprolactam, which counts for the 6 positions there. So it can be very awkward to try to figure out exactly what it's used. Now notice the first one right here, this is the IUPAC name. So this is very precise. We know exactly where everything is, but just looking at it, there's no way you're going to see that that's nylon 6. So the idea here is that we just need to be very careful and diligent about describing the polymer that we want to be talking about in a correct way that everybody understands what we're having. Okay, so The vinyl polymers most commonly are from what feedstock we used. So if we made the polymer from ethylene, we call it polyethylene, even though technically it should be called, polymethane or polymethylene, because we only have methyl groups along the backbone of the chain. So the fact that we call it polyethylene has everything to do with the fact that we started with ethylene, we polymerized it and turned it into polyethylene. And with tetrafluoroethylene, the same thing, polytetrafluoroethylene, PTFE. Or polypropylene, because we started with propylene here, even though technically it should be poly-1-methylethylene, it isn't called that because of the feedstock. And of course, styrene is the same way. So, and it gets even more confusing when we start to get into butadiene. Butadiene is used in a lot of natural rubbers, or I'm sorry, synthetic rubbers, instead of the isobutylene, which has a methyl group on it here. Here, isobutylene would have a methyl group there. But it can be polymerized in a number of different ways. We can actually just polymerize one of the diable bonds, and that's called a 1,2 polybutadiene. And then we can polymerize it where we have a trans configuration or a cis configuration. Not only are they polymerized all by different catalysts or different methods, they all have different names and they all have different properties, even though they're all starting with the same starting material, different properties, different reactivities, different names. So we have to be, again, very diligent about our polymer names. All right. So that's just the homopolymers. Now, what if you have a mixture of, oh, I'm going to do ethylene and propylene together because I want to change the properties not to be just ethylene or just propylene? Well, then that gets even harder, if not impossible, to identify them. So the idea here is that we kind of recommend a couple different things. If we don't know the exact distribution of the 2 different monomers or 3 different monomers we have in there, we just call it a copolymer. The reason we call it a copolymer is we know the feedstocks were in there. We just don't know where they exactly are, if they're alternating or if they're random or if they're somewhere statistically distributed in there. We don't know. So we just call it co. And so if you haven't analyzed it by some detailed method, most of the times everybody will just put co on there. However, if you know that you have the feedstocks and you put them in at the correct ratio at the correct times, that you have a random distribution, you can actually say that it's a random copolymer. And so you would, some things are better to be random than non-random. And then if you know that one has reactivity over the other, you might be able to say, oh, I know it's exactly alternating. Monomer 1, monomer 2, monomer 1, monomer 2, monomer 1, monomer 2. If you know it's actually alternating, and you can do that by different reactivities, et cetera, then you can say alternating right there. And then if you have a statistical distribution, so it's 35% butadiene and 15% styrene, you can call it a statistical distribution of those 2 monomers, okay? So if we look at the different ways to do that, whenever you see co, we really just don't know where it is, or we don't want to worry about whether it's alternating or not. If we're looking at something alternating, those tend to have different properties, okay? If we know we have a block of one monomer and then a block of another monomer, we call that a block. And we say that those are very common in non-ionic surfactants, and we'll actually be seeing those in some of our processing that we do. And then if we know that one of the polymers is going to be attached to a main chain. So you have a main chain going on here, and then the polymers coming off as like in a comb polymer, those are grafted on. We can actually say those are grafted on so that we can look at those different ways to do it. Now, once you get into 3 different monomers, then of course you have to use the same thing. If you don't know, co. If you know they're blocks, you use blocks. If you know they're alternating, you use alternating. Questions on that? So when you go to the literature and somebody says, I used this, they're hopefully going to have a description somewhere that says, oh, this is from this manufacturer, you can look up that manufacturer and know whether it's random or alternating or block. Okay. Okay. For the step growth polymers, it's even more complicated because sometimes it's based on what you started with, sometimes it's based on the functional group, sometimes it's just based on whatever the engineer wanted to name it that day or the sales team wanted to name it that day. So we'll talk about a few of those as we discuss them. Like polyethylene terephthalate is one of the ones that has a number of names that we can use. Okay, so these are ones that we should become familiar with because these are the most common that we'll see in this, in our nanocomposites. Specifically, starting with things like polyethylene right here, it's rarely ever just polyethylene. It's usually high density polyethylene or low density polyethylene. Okay, high density polyethylene has fewer side chains. Low density polyethylene has lots of little 4 carbon chains hanging off. And so it actually changes their properties. High density polyethylene is much more impact resistant, can be much more crystalline, can be much harder. Low density polyethylene tends to be easier to mold. Okay, polypropylene can be processed a couple different ways. It can be opaque or clear. And it has a really, because it's like almost all hydrocarbons, it has very low surface energy. It's very hard to get some of the nanomaterials to get them and be dispersed in polypropylene appropriately because there's no interfacial interaction between the polymer and the nanoparticle. So sometimes you'll see it's very hard to get it into polypropylene, but then they try something like nylon and it works great. So we should look at that as one of our systems. The polybutadienes right here, again, they all have different melting points, processing points, and different reactivities. So we'll see those all being used different ways. Polyisoprene, which is closest to natural rubber. Right here, it can be made synthetically. And then polyisobutylene is going to be with this 2 methyl groups here. It tends to be nice and sticky and tends to be used as a contact adhesive right here. And then of course, polystyrene is another common one we'll see used both in melt processing and in solution processing. But now we have 2 polymers at the end here that are actually unique in the fact that they can be made to be water soluble. Polystyrene sulfonate is water soluble in itself. So if you have something that you want to disperse into water, this would be one of the polymers that you would want to act as a dispersing agent or the final part here. And then the polyvinyl pyridines, and there's a nitrogen here and there's a nitrogen here. So this is the 4 and this is the 2 in here. When you put those in the presence of an acid like HCl or something like that, they become charged and they also become water soluble. So those can actually act as one of those basic dispersing agents where this is, slightly an acidic dispersing agent. So then we have acrylic acid, methacrylic acid. And so the difference between acrylic acid and methacrylic acid is this methyl group here. In acrylic acid, we don't have it. The methyl group would be attached to that same carbon. So that's acrylic acid and methacrylic acid. We tend to actually only have these partially hydrolyzed because sometimes it kind of makes it difficult there's so much hydrogen bonding, it's difficult to redissolve. Then there's methacrylic. So this has a methyl group instead of the hydroxide here, making it not water soluble. So these can be water soluble and these are not water soluble because we've taken that hydrogen bonding OH group off. And then PMMA is really common and for a number of different uses. Again, melt and solution processable, both of these are. Polyvinyl acetate is usually the way they make polyvinyl alcohol. And then again, when they make this, they hydrolyze off that acetate to give us the polyvinyl alcohol. Okay, and again, 100% polyvinyl alcohol is poorly soluble, so it's usually only 75% hydrolyzed to give us that. Polyacrylamide can be water soluble, and then polyacrylonitrile can be very tough and durable, usually pulled out into fibers and then pyrolyzed to give us carbon fibers as well. Okay, another common one is PVC, very tough until you plasticize it. And so a lot of people will do tougheners or plasticizers with it. Polychloroprene is used as an additive for an oxygen barrier, usually a lot. PTFE, tetrafluoroethylene, polytetrafluoroethylene. Again, that's the generic name. Teflon is the common name. Polyvinylidene difluoride. So basically this started with a vinyl group with 2 fluorines on it right here. And it turns out this is a piezoelectric polymer and also a decent barrier to water. In contrast, by putting chlorines here, it's actually used in saran wrap as an oxygen barrier and makes it kind of stretchy. So just that little bit of change from the fluorine to the chlorine changes its properties and its use. Styrene butadiene styrene copolymer here. It's a block copolymer. Starts with styrene, then you do a little bit of butadiene, then you add another styrene on the end of it here. Those tend to be really tough materials. And then this is a workhorse of the handheld devices industry, ABS plastic. It's tough, it's easily molded, it's fairly impervious to a lot of solvents. It's used a lot. So that's ABS plastic, is acrylonitrile butadiene styrene. All right, so those were all vinyl-based polymer systems. Now, if we go to the step growth one, we have one called polyoxymethylene. A lot of people call it polyformaldehyde, and the common name is Delrin. It's lubricious, and people use it as bearings for a lot of things because it slowly wears away. Then there's polyethylene oxide or polyethylene glycol. You may have heard it called PEG. PEG tends to have some number of units here, like it can be 100 molecular weight, 1,000 molecular weight, 10,000 molecular weight, but it typically has an OH group, a functional group at the end. PEO tends to only have functional group on one side versus the other. Okay, so then we have polydimethyl siloxane. So this is basically most of the silicones you use, unless you go to a high temperature silicone, is going to be this polydimethyl siloxane. And there's a bunch of different ways to cure that. And we'll see a couple of the composites actually use this in here. If you're looking at high temperature ones, they start to replace this with a phenyl ring to give it a little more high temperature strength. This one right here is used a lot in electronics for packaging. It's polyphenylene sulfide. So it's like a benzene, it's like an ether, phenylene ether, like this one here. This is again used in a lot of packaging because it's not very soluble, but it's melt processable. Okay, and then this is, the general term is polyurethane because of this urethane linkage here in the middle. It can be made a number of different ways, both as fibers, plastics, foams, films. That can be made in a number of different processes, but it's this urethane linkage here that names it. Then this one's kind of neat. You'll see them a lot. PEEK for tubing in high pressure situations, and it's a polyether ketone. And technically the PE, it would be PEK for polyether ketone, or polyether ether ketone would be PEEK. So by adding the E, it shows you how many ethers there are along the backbone. This is the most common polycarbonate right here. It's made from bisphenol A and usually phosgene, but they have a new way to make it with transesterification. This is a really big one. It has those two acronyms there, PET for polyethylene terephthalate, but a lot of engineering people call it polyethylene terephthalate ester. So that's PETE is the other acronym. They both mean the same polymer, and so but they are usually they're used interchangeably. If more engineering, they're going to use the PETE. More chemistry, they're going to use the PET. Polyether sulfone, the poly-EI, which is ether imide, and polybenzimidazole are all high temperature polymers. You're going to look at these for electronics packaging, circuit board coatings, and films used to insulate batteries and stuff like that. So all of these are high temperature processing materials that we'll see And we can change their properties again with our nanocomposites. I want to introduce a couple electroactive polymers because we'll see a couple of these. They're used a lot as an additive and to make things more soluble. Things like this right here, which is polyaniline, P-A-N-I, PANI. That's used extensively in the system. This one right here, polyedot, P-dot right here is used. In fact, there's even a one with a sulfonic acid group on here that's water soluble that makes beautiful blue, highly conductive films. And then let's see, this polyphenylene vinylene. Those are the three electronic type polymers I want you to see. These are used a lot in photovoltaic devices as the charge transfer agent. So these three in particular, you should pay attention to. We're going to see several papers over the course of this semester where those things come into play, specifically when we're talking about improving the electronic properties or the static dissipation properties of a device or product. All right, questions on the polymers that you should know, or at least just be familiar with. Okay, so there's also some trade names associated with this. So like I said, Teflon is polytetrafluoroethylene. It's actually made, most of these are actually made by DuPont or Sabic, so they're kind of easy to identify. If you have high density polyethylene fibers, it has to be high density polyethylene fibers. We call that Tyvek. And Tyvek is usually used as a non-woven fabric, either as jumpsuits that help, decontaminate you, or they're used to wrap houses. Kevlar and Nomex are two aromatic polyamides. And the difference is one is 100% 1,4, and the other one is 100% 1,3 in their position. And so they process differently and they're used differently. Kevlar has a much higher tensile strength. Nomex actually works better as an anti-flame fiber. So Kevlar and Nomex, even though they look very, very similar, they actually have two different uses, and they are typically used as fibers. So Kevlar and Nomex are their fibers, and both are again from DuPont. Styrofoam is a specific kind of polystyrene. The styrene itself has to be puffed up with a blowing agent to give a closed cell foam, typically in beads, and then you reprocess the beads afterwards with steam. So styrofoam is actually a Dow chemical trade name. Noryl is the polyphenylene oxide polyphenylene sulfide. And that's used a lot because mixing them together, actually, it's a very lubricious polymer. And so you can use it in between two things that rub against each other, and it'll be used for that. Kapton is a polyimide or a polyether imide by DuPont. It's typically those, yellow high temperature films that you see. Kynar is the polyvinylidene difluoride. Okay, Kynar it's a piezoelectric material, so it can interact with, we'll talk about piezoelectrics later. Lexan is the polycarbonate used in bullet resistant or damage resistant windows. Lucite is PMMA or plexiglass. Both of those are less durable than Lexan, but they are also used in window type applications, transparent window type applications. Saran wrap is actually a copolymer with the polyvinylidene dichloride. So the difluoride is the Kynar, which is a piezoelectric material, but the dichloride is actually used in there as an oxygen barrier and actually to help a little bit of structure. And then Udel actually can be made in film, foam, and block as a high temperature polymer. So use temperature at 300 C for 365 days a year. So those are all very common trade names. And here's the structures of all of those, just in case. I'll post these on Canvas site, so you'll see that those have. So we have the different structures. We have the vinylidene fluoride, the vinylidene chloride. We have this as our Kapton, as our Kevlar, and showing why it's so strong because of intramolecular bonding. And then this is our Kapton right here. And this is our polyether sulfoxide, which is K, the sulfone right here, UDEL. All right. Okay. Any questions on any of those? So it'll be important that as we go through it, as you're doing your review or your presentation, that if you use a trade name, go ahead and pop up a structure so that everybody can be on the same page when we do that. So in the past, polymer recycling actually was working okay, but it's a little bit harder than it used to be now. And the reason is that there's so much coming in through the recycling process that there's not really a market for it. So it's actually slowed down a bit from where you have it, even though we have this segregation where we have the PETE, so polyethylene terephthalate, the high density polyethylene, low density polyethylene, polypropylene, polystyrene, and other. And then I don't know what the V stands for. I think it's other vinyl polymers, like PVC. So even though there were segregations like this, the actual sorting, separation, cleaning, and reprocessing, the materials reprocessed from specifically post-consumer recycled are never as high as they are for the as-produced polymer. There's always some kind of impurity or decomposition or change in property going from the as-made material to the post-consumer recycled. So there's always a little bit of, but some things still can actually be used very well in this. For example, PETE, which can be recycled, is probably the best one that's used to get to something like carpets and clothing and non-woven road mats. And so even though polyethylene, it has a higher market share, the actual polyethylene terephthalate is actually the higher end use of this recycled polymers. Okay, questions on the types of polymers that we're going to look at? Okay, now when we get to the different things of incorporating different nanomaterials into different polymers, what we're going to look at is what kind of interaction the polymer has with the nanomaterial. And if there's a strong interaction between polymer and nanomaterial, we're going to see an enhancement of the properties we'll see. If there's a weak interaction between that, number one, they're going to be harder to evenly disperse, and there's going to be less of an effect. So kind of when we start looking at nanomaterials versus a polymer, we need to remember what the polymer structure is, or go back and look what the polymer structure is and see whether or not it's going to be enhancing an interaction between the two, or not have a good interaction between the two. And that's going to tell us whether or not there's going to be a good enhancement or a poor enhancement. Okay. All right. So let's go ahead and start talking a little bit more about molecular weight and how we can define it and determine it, because it has such an effect on how things are processed and what the final properties are. So basically, our molecular weight tends to be in the thousands to millions of grams per mole. Okay, so for example, I have a polymer I'm making in the lab right now. It's about 32,000 molecular weight. If I go above that, it gels out and never redissolves. If I go below that, it kind of powders out. So I have to be very precise about trying to get it exactly at the right place. But things like polyethylene, you want it in the millions. It's tougher, it's better to, it's easier to deal with. Okay, but there is a problem. If you get too high a molecular weight, you do get those better properties, those toughness or the high conductivity or the tensile strength. But as they get to higher molecular weights, they tend to be less soluble and have higher melt viscosity. So they're harder to process. So that's kind of an important part of it. As they do, you have to find that balance between processing and properties. Okay, molecular weights of low molecular weight of like small molecules that we call them, or individual monomers, are usually determined by mass spectrometry, because we can volatilize it and send it through the spectrometer and get an exact mass. However, polymers can't be volatilized. They're just way too big. So we typically have to use some kind of different thing to look at their molecular weight. Now, in the step growth polymers, we rarely see just one kind of polymer. We'll see one with 100 units, one with 102 units, one with 110 units, because they were growing in stepwise fashion. It's not just going to be one of those. And even when we do our chain growths, depending on when they started growing, they're all going to grow at the same rate. But if they started growing at different times, they are also going to be of different molecular weights: 1.2 million, 1.1 million, 1.3 million. So we have to think of it, the molecular weight of a polymer, not as an absolute number, but as an average of the molecular weights. And there's a couple different ways we can calculate that. Okay, so the first one is what we call the number average molecular weight. And that basically means we actually sum up the number of molecules that are this molecular weight and the number of molecules that are that molecular weight and the number of molecules that are that molecular weight, and we divide it by the sum of the number of polymers we have. And so basically what it's saying is we have our number average molecular weight because each and every molecular weight is weighted the same. My million molecular weight and my 500,000 molecular weight all have the same weighting in our number average molecular weight. Okay, however, because we start to look at properties are influenced by the higher molecular weights, we have what we call the weight average molecular weight. In the weight average molecular weight, what we do is we square the molecular weight and then multiply it by the number that are those. This means that when we square it, means the higher molecular weights tend to influence the number we get out more. So the lower molecular weights, even though they're squared and added into the system, they're not going to be as big as the square root of the higher molecular. So imagine instead of just taking the average of it right here, we're shifting it to the higher molecular weights. And so that means that M sub W, the weight average molecular weight, is always bigger than the number average molecular weight. Okay, so because we have the squaring of the molecular mass makes it scale to that higher molecular weight. So how do we use that to our advantage? Well, because M sub W is always bigger than M sub N, and if we divided M sub W by M sub N, it would always be greater than 1, we can actually get what we call our Polydispersity Index. Okay, so all right, let's say we have a very big wide distribution, right? And so our M sub N comes out to be, something like 500,000. And then our M sub W comes out to be 1 million. Okay, so if we divide these two, we're going to get a polydispersity index that's pretty wide. Okay, so let's say if we had polymerization, we did it by a different mechanism, and we still had our N sub N was at 500,000, but our M sub W is now at 600,000. So now we have a narrower difference between the weighted average and the number average. So we have a narrower polydispersity index. Okay, so that's what we have here in the polydispersity index. Tells us something about the distribution of the number of polymers we have. If we have a very big distribution, our polydispersity index is big. If we have a very narrow distribution, our polydispersity is very narrow. In fact, if you get to perfect things like proteins or starches, they tend to have only one molecular weight. And we call that monodispersed, meaning the M sub W and the M sub N are exactly the same because you don't have any variations. The protein is exactly 750,000 Daltons, and that's the only thing you see. Okay, so polydispersity tells us basically how many different chain links we have in our system. Now, for step growth polymers, it's pretty common to have a polydispersity of 2. Okay, because if you think about it, you are adding monomers, and then those are combining and combining and combining. So statistically, it turns out that you're going to have about half of them a little bit bigger than the other half. And so our polydispersity usually runs right around 2. Chain growth polymers can actually have really big polydispersities. You can have 1,000,000 and 500,000, depending on when the chain started growing. And then if we have a different polymerization system, what's called a living system, that's where you started every chain at the exact same time and you stopped them at exactly the same time. In that system, you have a very precise number weight average, and the number average turned out to be exactly the same. And we have a low polydispersity, or a polydispersity of 1. Okay, do we understand polydispersity and what it means when we're looking at how many different sizes of polymers we have in a polymer system? Because what we're going to see is sometimes, they'll list the polydispersity, typically only if you're making a new polymer, but it does kind of give us a little bit of variation on some of our properties. So we might see it from time to time. So if we're talking about molecular weight, so how do we find molecular weight? Well, there's a couple different methods. One is called the absolute molecular weight. One's called the relative molecular weight. Okay, an absolute molecular weight is where you actually determine the exact molecular weight of individual molecules, and then you have the absolute number. And this has to be done by a colligative method, which means it doesn't matter what about your sample size or your process or anything like that. The number it's going to give you is going to be exactly the same every time. And the techniques we use for this tend to be very expensive and very time consuming. For example, in-group analysis. We can do in-group analysis. Typically, it's done by NMR. And these NMR experiments can last for 6 weeks. I went and visited Shell, and the guy was running the 500 megahertz NMR on atactic an isotactic polypropylene. He says, yeah, we've been running about 6 weeks. We almost have enough data. It's like, wow. And they're trying to get the absolute molecular weight of the metal. The other way to do it is look at osmotic pressure, because osmotic pressure is a colligative property. It doesn't depend on the actual number of polymers. It just depends on the molecular weight. Then light scattering, if you can get your polymer into solution, because light scattering, there's a dynamic amount of expansion and contraction in these polymers, and you get the average of that, and that gives you the number average molecular weight in an absolute way. And then there's MALDI, which is matrix-assisted laser desorption ionization. So basically, you put your polymer in something like nicotine that's easily volatilized. You hit it with a laser, and that blows all of your polymer particles into the gas phase. Notice we didn't volatilize the polymer. The polymer itself cannot volatilize. It would be impossible to have enough energy to make it vaporize. So what we've done is we've blown it into the vapor phase using some other thing, that's the matrix. And then once it gets blown into the air, it can actually then go through a mass spec and analyze it for exact molecular weight. And then a very old way, but a very tried and true way, is what we call ultracentrifugation. So in centrifugation, the more dense material ends up going to the higher centripetal force area, or basically the bottom of the centrifuge tube. And what you do is you literally centrifuge these things for days, and then you take different layers and you can actually get the different molecular weights of the different layers to give you absolute molecular weight of your system. Now, all of these are expensive. Almost nobody ever does these. So most of the time we actually use what we call relative molecular weights. Relative molecular weights are good enough for most things. Okay, if you really need an absolute molecular weight, then be prepared to spend $20,000 to get that. But relative molecular weights just give you a great comparison between a set. Let's say you have 3 samples of polypropylene, you run them all on the gel permeation chromatography or GPC, and you'll say, okay, one's a little higher molecular weight, the other 2 are a little lower molecular weight, so relatively, I want to use this one because, okay? Another way to do this is solution or melt viscosity. That also works very well with things like polypropylene, polyethylene. You'll do what are called melt viscosity tests, and that gives you a really good relative determination of molecular weight. And then there's vapor pressure or gas phase osmometry, which is looking at how fast things volatilize out of the system. And that usually gives you a pretty decent way. These tend to be much faster, less than a day to do the experiment, much cheaper, they can be done in the lab, and you don't have to have any external validation. With gel permeation chromatography, you tend to have something like a polystyrene standard or a standard that is of a molecular weight, hopefully in a greater range than the one you're looking at. So you can say, my polymer is it has 50,000 molecular weight compared to polystyrene standard. And that's a lot faster than trying to get an absolute measure. Okay, questions comparing the difference between absolute and relative molecular weight? Nope.
Yes, sir. I have a question.
Yes.
These 2 methods of determining the molecular weight, are they dependent upon the application? Like, for example, if you need the accuracy in an application, then you must go for the absolute one.
Let's see. Is it based on application? Typically not based on application, but sometimes you will have, let's see. It's not usually based on application. It's based on things like how confident you are that that is, the exact molecular weight you have. For example, if this is a polymer you're about to go use to industry and you've only had relative things up to now, you might want to get an absolute molecular weight to see how far you were off your relative molecular weight. It's usually only done for, things where you want to be really precise, like maybe you're trying to patent something, or you're trying to, compare the difference, or you're trying to crystallize a polymer to get a perfect crystal structure. Most of the time, relative is usually good enough.
And so in the end of the slide, you have written that we have to compare the relative one with the standards to get the absolute molecular weight. So would there be any, any error after doing this procedure or not, sir? Like after comparing with the standards?
Oh, yeah, there can be error. So when measuring the absolute molecular weight, if you end up measuring the absolute molecular weight, what you're going to see is, like, say you, okay, let's see, where is it? My slides are not showing up here. Are my slides showing up on there?
No.
You might have to switch it to share screen instead of sharing the presentation.
Okay, share screen. Let's plug my cable back in. My cable's in. I trust this computer. What? It was playing earlier. All right, hang on. Done. So, okay, what it was trying to say on there is that, let's say you do actually do an absolute molecular weight determination, and you find out that you've been saying, oh, I have 50,000 molecular weight compared to polystyrene, okay, up to now. And then you did actually do one set where you did get absolute configuration, and now you can compare that directly. Now you can say, oh, well, actually, it turns out our polymer was 75,000, because when we compared it to the absolute molecular weight, it actually had different properties than comparing it to the polystyrene. And so that's where you take the absolute molecular weight, and then you readjust your relative molecular weight to the known absolute molecular weight. That's what that statement is trying to say. Unfortunately, I can't. Let's see. Share new. Share. Keep saying trust the thing. Okay, well, let me pull it up over here then. Okay, let me go over here then. I'm having, don't know why my iPad decided to not share anymore. But let me get back to that slide. Here we go. Stop share, share again. PowerPoint, share. There we go. Can you see my slide now? Okay, so right here, determine the absolute molecular weight from a relative standard requires comparison of standards that measure using both methods. So that means that, let's say you use polystyrene standards, right? Then you use polystyrene standards that have been measured by some other method, colligative method or other than that. Then you can say, well, okay, based on the known, the absolute, and the comparative, I can confidently say it's this. So you're using two different methods to verify your molecular weight. Does that make sense? Okay. All right, now that I have, okay, I'm gonna have to do it this way. I can't, there we go. Okay, so I said molecular weight's important because it's gonna change our melt properties, our solution properties, and kind of our toughness, overall toughness. But once we get over this molecular bridge, we can actually start looking at some of their other properties. And so now I'd like to switch gears a little bit and talk about chemical structure versus polymer morphology and how polymer morphology changes the polymer properties. And so this is going to go a little deeper into kind of what we're talking about, specifically, you know, molecular weight changing properties, et cetera. So there's a bunch of different things we need to look at. First thing we have to do is define polymorphology. So polymorphology isn't just the structure itself, it's how the polymer is arranged within itself. So let's assume that you have all your solvent out. So how are those polymer chains interacting with each other? Okay, so if these polymer chains are just kind of stacked together and not really having strong intramolecular forces, we tend to call that an amorphous polymer, meaning that there are no strong ordered sections. There's no little places where you can see a repeating order of these units stacked on top of each other. And what we call this, especially if the polymer is a rigid polymer, but it has no crystalline sections to hold it together, we call that a glassy polymer or a glass, okay? So because it's not crystalline, because it's amorphous like glass is in its plate glass state, it is not crystalline, and so we call it a glassy state because it's not in a rubbery state, because the rubbery state is when it can move. Glassy state is when it's fixed but still doesn't have crystals in it. In the exact opposite of that, let's say you have something where you can hydrogen bond or have a very easy to do a periodicity. So these are stacked on these, are stacked on these, and you have those going all the way through the system. That's considered to be a crystalline polymer. You have to have a regular arrangement of how they are stacked together. But since it's really hard to get all 100% of the polymer, typically you call them semi-crystalline or mostly crystalline polymers, okay? Now, the other thing is that glassy polymers, amorphous polymers, tend to be more transparent than crystalline polymers. Little teeny crystallites in the polymers tend to make them opaque. So you can actually have like polyethylene that has almost no crystals in it and it can be very transparent. But then polyethylene, because it can crystallize very easily, tends to be opaque. So you're going to have a lot of crystals in it. So you'll see the difference between the amorphous glassy polymers and the crystalline or semi-crystalline polymers because of the transparency. The next kind of thing we have is what we call a viscoelastic polymer, meaning that it can stretch and come back. So it has the property of a solid, being that it doesn't flow, but it has the property of a liquid because we can stretch it, and then it comes back to that property of the solid. So we have these, a little bit of both. So this is in what we call the rubbery state or the viscoelastic state. All right, I gotta turn my iPad off here. And then, all right, so, so now once we have, those are the substructures within the polymer system, and they can be crystalline or non-crystalline. So now let's start to deform these things in a couple different ways. So the first thing we can do is we can call tensioning. So tensioning is when we pull it in an axis, and that is an attempt to stretch the material. And that resistance to stretch that material can give us the tensile strain or tensile strength. So tensile strain is how much force is applied per unit area. So there's typically a force and area term for that. That's tensile stress. Tensile strain is how much it deforms. So you start with, it is at this amount when we started and this amount when we end. So it's usually a unit per unit. And we'll see that on the graphs we have. Modulus is the stress versus strain. So the stress versus strain gives us the resistance to deformation. The tensile strength is when you've stressed it and strained it so much that it breaks, or the maximum load it'll take before it breaks. That's what we call its tensile strength. So if you imagine you're pulling and pulling, and then it breaks, that load right before it breaks is what we call that tensile strength. Now, tensile strength is all about stretching it or going in a single axis. Impact strength is different. Impact strength actually has to resist a much higher load per unit time. Okay, so if you can imagine, you can pull something and it'll stretch like silly putty. It'll stretch, so it has this deformation it'll do, but you hit it with a hammer and it shatters into 1,000 pieces. So the impact strength is how much strain versus a very short period of time. Tensioning tends to be over a longer period of time. Okay. Now, let's say we're not actually moving this, we're not changing this, but we're trying to move it without changing. So tend to, like, instead of pulling it, we're kind of making it shear across itself. And then we call this the shear modulus. So imagine a rubber that can easily, resist the movement of side to side. That's what we call a shear modulus, which is different than creep. Shear modulus actually has a load applied at a specific frequency. Creep is where you have a load applied over a long period of time. Creep is when let's say you put 100 pounds on top of this disc, and it slowly spreads out over the course of days or years. That is what we call creep. Shear modulus is just the resistance to flow in a short period of time. Creep is the resistance to flow in a long period of time. And then there's also stress relaxation. Let's say you're pulling on this thing and you let go. Some things are going to stay exactly there. Some things, when you stress them, are going to spring back. And if they spring back, that is what we call stress relaxation. Okay, so rubbery things tend to have stress relaxation. Brittle things tend to not have stress relaxation. So how can we tell the difference between a rubbery polymer, a strong polymer, a weak polymer, just by looking at their stress strain curves? Well, they have some pretty typical ways to do it. And I can't read this one right here on this one, but there's some older terminology for these things. But the idea here is that if we look at the stress, which is the force delivered, versus the strain, which is the deformation right here, let's say we can have a very high stress, but very little deformation, and then we have breakage. That indicates we have a brittle polymer. We're going to pull as hard as we can, and then all of a sudden it's going to break, but it's not going to move very much. That's a brittle polymer, but it's a strong polymer because it resisted a significant amount of stress. Okay, so most plastic polymers, specifically amorphous or semi-crystalline ones, will have what we call a initial modulus, which is this part where it's resisting strain, and then it's going to have a break point where it starts to flow because of strain. So it's going to resist, and then it's going to start to flow, and then at some point it's going to fail. And when it fails, that right before it fails, that's the ultimate tensile strength of the polymer. Right before it fails, we get that number. Now let's say we have something that immediately deforms upon applying stress. Then we're looking at an elastic material or a rubbery material where we can just have it continue to grow and grow and grow until it reaches its ultimate slippage of the chains and it fails. That's where we have what we call an elastomeric polymer. So think the first one would be something like an epoxy where you can strain it and then all of a sudden it breaks. The second one is where you can strain it, and then you have to bend it and pull it, and then it finally breaks. Or then you have one that just goes, and then finally, eventually, it'll snap when you extended it very, very long. Now, elastomeric polymers can go almost 1,000 times their initial length for the elastic materials. Plastic materials tend to only do it a little bit over 100%. Okay. Questions on the stress strain curves. So a lot of people will say, hey, show me the stress strain curve, and you'll see if a material is tough or not. So what does it tough mean? Well, tough means it has a certain amount of modulus and then a certain amount of strength at the end. So in here, we only have modulus right here. It just resists force until it breaks. Here, this is our initial modulus, but then it still has additional strength after that. After it starts deforming, it still has strength. So that tends to be a more tough material. So brittle material, tough material, elastic material. All right, questions on that? And one thing I do want to show on this curve over here is the modulus. And I said that stress is force per unit area. So notice stress is under PSI or pounds per square inch. A lot of the time it can also be megapascals, which is also has an area component, but then strain is inches per inch or unit length per unit length. So those are important parts of that. All right, so question?
Yeah, so the ductility of the polymer would be seen in the plastic polymers, right?
I'm sorry, repeat that, please.
The ductility, for example, if the polymer represents a ductile behavior, will it come under the plastic polymer?
Ductile can be two things. There can be ductile tends to mean that it can flow under force, or it can be deformed under force. And it depends whether it typically would be that middle curve there, where it has some resistance to flow and then it does flow, becomes ductile. And so it'd be this part of the curve where it is, quote, ductile. But here it's resisting moving until it is at the force where it can be deformed. And so this would be the ductile region. All right. So
I got one question.
yes.
Where does the durometer of the hardness come into play when you're dealing with rubbery material?
Okay, durometer hardness has everything to do with how much force it takes to indent. So if you can imagine that, let's say most durometer are actually these little gauge things, and they have little probes. And what they're looking for is how much that probe under certain amounts of force can poke into that material. So we were looking at the resistance to flow with a backer. So the entire sample here is backing the resistance here. So it's not just if you had a thin one, how much it would deform, it's how much that is deforming with all of its elastic material behind it. So all durometer readings are talking about how much a probe can penetrate into a rubber material at a specific force. And so you have multiple durometers, like a durometer 50 is a little bit firm, but a durometer 75 would be firmer. And so the penetrometer would go in less distance. Does that make sense? Okay. So, and then there's actually several different there's several different types. You can do an ASTM A, B, C, and D. And so you can get different durometer readings for each of them. Most of those are force and the shape or whether the penetrometer is domed, pointed, or flat. And so you can change the different penetrometers versus the different forces. And so that's what the different ratings mean.
Okay, so we're not looking for a failure point when you're dealing with the hardness. It's just the penetration.
No, and it should be a rebounding penetration. It should not be a permanent deformation. So you put it on there and you should be able to do it multiple times and it should rebound.
Okay, thank you.
So it's not a failure test. It's a reproducible springback test.
Spring back.
I'm sorry, it's not because it springs. You don't measure springback. It just should spring back. All right. So now we have polymers can be crystalline or amorphous. Polymers can be long or short, but there's also, those different polymer chains look differently. So we have, let's see. Okay, good. All right, got 12 minutes left. All right. So how are the polymers like right? So if you think about it in an amorphous polymer, the polymers are probably all kind of going off in all different directions, right? And so there has to be a way to describe, what an individual polymer is doing versus what multiple polymers are doing, which is what the bulk of the polymers are doing. And we call those different types of the structure. So we have different structure levels. So a primary structure is just, what does the polymer look like? What is the repeat unit, right? So if the repeat unit is, going, zigzaggy or whatever, that repeat unit is what we call a primary structure. So this is going to tell us things like, will it hydrogen bond? Will it do this? Will it do that? Okay. So, but that doesn't tell us how it's going to interact with other polymers, right? So then we have to look at the secondary structure. The secondary structure is, does the polymer want to form a helix? Does the polymer want to form a coil? Does the polymer want to be completely straight, right? So some polymers like polystyrene like to have a coil in them because the phenyl groups all go to the outside. And that would be what we call the secondary structure, okay? So the primary structure is whatever the polymer is. The secondary structure is how it wants to form itself, trying to space itself out as much as possible. A lot of things are helical, a lot of things are coils, some things are very straight, like rigid rod polymers tend to try to be rods or kind of ribbons. And so we'll see that as our secondary structure. But then we have a tertiary structure, is when they start folding on top of each other, can they crystallize? This happens particularly during crystallization. And the size of the crystal depends on whether or not you have a very flexible unit in your backbone. Let's say you have an ether in your backbone. Well, that'll let it fold over partially, and then you'll have another one that can fold over again. Then they'll crystallize, and then it'll fold over again and crystallize and fold over again. So we have this contour length, this maximum length that the polymer chain can extend, but then be able to fold over on itself. And when it folds over on itself, that gives us our tertiary structure. Okay, so just the polymer itself is primary. How the polymer would be in solution, whether it's helical or straight, which is secondary, how much they fold over on each other is tertiary structure. Now, this also gives us in solution, a tertiary structure would be, so it's trying to be helical, but it's dynamic, and so it's going to move around. And so by light scattering, we can actually measure the root mean distance, end-to-end distance. And that's actually giving us a good way to measure molecular weight. But that's because it's a tertiary structure. It's actually trying to be a secondary structure, a primary structure, but then it's trying to fold in on itself because it wants to interact with itself. So we can use that to our advantage to measure its molecular weight. Now, the quaternary structure is the overall shape of all the tertiary structures. So we have these little things folding over on each other, and how are they stacking together? Are we stacking together in random blocks, so it's semi-crystalline? Are we stacking together in regular blocks, so it's very crystalline? Are we stacking them together in bundles so they make fibers? That's our quaternary structure, how the different fold over sections meet together, okay? So, and all these different levels actually change properties. Once you have a very rigid primary structure, that's going to dictate how your secondary structure, whether you're helical or ribbon or straight, then those are going to determine whether or not you can do a fold over, a shaping, or a bending on your system. And then how those fit together, all of those bigger structures fit together, will determine what our final properties are, our quaternary structure. Okay, question? All right. So let's see. All right, so now when I started talking about polymers, I said we really need to pay attention to what the polymers are because it'll change how they interact with the nanomaterial we're going to put in there. So now we have to look at the molecular interactions of these things and how they interact with themselves and can interact with other things. So the idea here is we need to think about, number one, what kind of primary bonding. Primary bondings are going to be ionic and covalent bonds, okay? The ones that actually give us structure. Ionic bonds tend to be much, much stronger than covalent bonds. And they tend to be, you know, a negative charge, positive charge interaction, or even metallic copper metal atom to atom bonding. That's the strongest one we can see. Now, this included in the primary bonding is what we call covalent bonds, which is what we see in all the polymer chains, the carbon-to-carbon bonds, the carbon-to-hydrogen bonds. Okay, so that's primary bonding. Those are the strongest and give us the strongest interaction. But, you know, so imagine our chains are being pulled on there. Okay, now we have our secondary bonding, and that's bonding between polymer chains or within two halves of a polymer chain. This secondary bonding is where nanocompositing becomes tricky, because you need this secondary bonding to have a good dispersion of your nanomaterial into your polymer system. So we have to look at those very carefully. So we have several different types. The first one we have is what we call van der Waals forces, which are very, very weak. Okay, it's an induced dipole. So imagine it's something like a waxy polyethylene coming up to a waxy polyethylene. There's no polar groups, there's no functionality, there's no strong interaction between the two chains. They are just, well, okay, we're very similar. We're just going to kind of line up together. We're going to have this weak force, and this weak force is going to be what we call our dipole-dipole interactions. This leads to the crystallinity in polyethylene, but it also leads to the kind of rubberiness of it and the waxiness of it. It's not a very strong interaction. It's the weakest interaction we have in secondary bonding. Okay. Now, if we have something with a polar group, like a polyethylene terephthalate, where we have that carbonyl, we have a permanent dipole. We have a positive side of that carbonyl and a negative side of that carbonyl. So we have a permanent dipole. And that dipole on this chain can interact with the dipole on the next chain, which can interact with the dipole on the next chain. We get this dipole-dipole interaction, which is a much stronger interaction than the induced dipole. And imagine we can use that to our advantage when we are trying to incorporate a nanomaterial. Let's say our nanomaterial has a negative charge surface. Well, we would like to have a polymer that has a partially positive or a positively charged component in it, so it can counterbalance that charge and really interface with that particle really, really well. So if we don't have that, if we have like polyethylene and we're trying to put a charged particle in there, there's nothing on the polyethylene to help balance that charge. It's not going to interact with it very well. If we have a dipole, it'll interact with it even better. Okay. But now let's go to our strongest interaction we have in secondary bonding, which is what we call hydrogen bonding. So if you have an acidic hydrogen somewhere on your system, like the polyethylene, the polyacrylic acid, the polymethacrylic acid, or the polyvinyl alcohol, those all have strong hydrogen bonding and interact with the material. If it's something that can be hydrogen bonded to, something that has a negative charge, it'll have the strongest secondary interaction that we can have. So we'll see a lot of opportunity where we see somebody tried something that doesn't hydrogen bond and something that does hydrogen bond, and they'll see a much better dispersion in the system in one versus the other. So this intermolecular interaction is going to be important. Okay. All right, let's see. And then, so that is the interactions that are chemical bonding. So we have the chemical bonding and then the secondary chemical bonding. Another thing we have is what we call chain entanglement. Okay, So let's say we don't have any other interaction and we have like very short chains, okay? And so we have these very short chains and they're kind of mixing together. And then you try to pull them and they just pull apart because the surface area of resistance from one to the other is very small, okay? Now, let's make those 10 times longer. And now, and you're pulling on them and it's pulling and pulling and pulling, and you have to pull all the way along 10 times more surface. So this one's going to have higher tensile strength than this one because the chain length entanglement is much, much longer. Now, there's a critical chain length that is required for this chain entanglement, okay? And it changes based on the polarity and the type of polymer you have. If it's a helical structure, it can be a little shorter than a straight structure, okay? So what we'll see here is that the number of repeat units required to do this can change based on polymer system. So for PMMA, even though it has dipole-dipole interaction, it has a structure that it lets it slip across each other. And so it has 208 repeat units are required for it to have maximum tensile strength. Polystyrene, because it's helical, these are larger volumes, and so they kind of slip past each other a little bit easier than the PMMAs, which are more straight, and therefore it has a higher critical chain length of 730 repeat units required. Now, for something like isobutylene, because they can slip and stretch and slip and stretch, isobutylene is also fairly high at 610, because imagine you have the possibility of having cis and trans. Those can lock into each other a little bit, but they are elastic enough that they'll slip past each other, slip past each other, slip past each other. So it has a long minimum, a critical chain length. All right, we see how the chain length affects that system. All right, I'm going to do these last two things and then we're off for the day, but I'll see you back on Tuesday. So viscosity. Viscosity is the resistance to flow. Now that's a bulk property. Chain entanglement is a microscopic atomic property. Viscosity is a bulk property where all the chains are moving together, okay? So all of the molecular interactions combined determine the viscosity because they're trying to all move together. So things that resist flow are viscous. They're not thick. And so, and there's different ways you can do that. You can do it in solution or in melt. Both of those count as viscosity. And the last thing I want to talk about is flexibility. Flexibility is different where, for example, in the case of polypropylene, you can have your chains all mixed together. You can do some kind of deformation, and then the chains will have enough energy to slowly move around and reorder themselves. So you can actually take polypropylene, do a surface treatment on it, and it will overnight, it'll rearrange and move, reorganize itself so it has the same surface it had before you surface treated it. So that flexibility, that intramolecular flexibility changes with the different polymer types. And it's all about how much you can, how flexible your units are, how many degrees of freedom of rotation. Freedom of rotation gives us our flexibility. All right, I'm going to stop there. We're right here at 3:20, and I will see you back here on Tuesday. All right.
All right.
Thank you.
Have a good weekend.
All right, I'm going to stop